Okay, finding limits analytically. So in this one, we're going to talk about the several methods we can use to analyze limits. Most importantly, especially in these notes, we're going to talk about direct substitution. There are several other ways, and we will talk about them when we get to them. The basis here is that we always want to try direct substitution first. Okay. If after we try direct substitution and we end with something where 0 is in the denominator or we get infinities, then we have to use another technique to simplify before we can substitute. For each of these examples, we're going to simply be able to substitute and get an answer. So for this one, we're going to solve this limit by plugging in 2 in for all the x values. So this is 3 times 2 squared minus 5 times 2 plus 4, which gives us 6. Okay, for b, I'm going to plug in 2 for each of the x values. So I have 2 cubed plus 1 over 2 plus 1. This gives me 8 plus 1 over 3, which is 9 over 3, which gives me 3. C, I plug in e for x, so I have the natural log of e over 3e. Natural log and e are inverses of each other, which means they cancel each other out. So natural log and e goes to 1, so it's 1 over 3e, and that is my answer. Okay, for d, I'm going to plug in 4. So I have the cube root of 4 plus 4, which gives me the cube root of 8, which is 2. Okay, for e, it says the limit as theta approaches pi 6 of sine 2 theta. We plug in pi over 6 into theta, so this is sine of 2 times pi over 6, which is equal to sine of pi thirds. You can either give me the exact value, which is the square root of 3 over 2, or the decimal, which I believe was 0.8660. Correct me if I'm wrong there. But whatever that is, put into the calculator. Okay. For f, we're going to plug in 5. So this is log base 3 of 5 plus 4, which equals log base 3 of 9. And if you recall from your properties of logs, we're trying to find 3 to what power gives us 9. And that is why our answer is 2. Okay. So let's say we're trying to solve limits, and when we plug in our values through direct substitution, we end up with 0 in the denominator. That tells us that we have some type of discontinuity in the function, or in other words, a hole. So if you recall from pre-calculus, remember, in order to find the discontinuity of a rational function, we first have to factor. Okay. And then once we factor, we should see if a point of discontinuity occurs and remove it by canceling. So we're seeing if anything cancels. Okay. And then if we have a non-removable discontinuity, we know that this occurs if they don't cancel. Okay. So the big thing here is that we're going to factor, and then we're going to cancel out the discontinuity. Okay, and this could be different on your paper. Remember, I had you do this in class with your groups, and you guys were writing this in your own words. So showing this is called the cancellation technique or the factoring method. And if we were to directly substitute 2 in, we would notice we would get a denominator of 0, which we do not want. So what I'm going to do first is I'm going to factor the numerator and the denominator. So I have x plus 3 times x minus 2 on the top, and x minus 4 times x minus 2 on the bottom. Notice how x minus 2 cancels out, which means that is where our point of discontinuity would be. And so now I just need to find the limit of whatever is left over. So I have the limit as x approaches 2 of x plus 3 over x minus 4. This is equal to 2 plus 3 over 2 minus 4, which gives me negative 5/2. Okay. We're going to continue and show this graphically. Okay. So we just found this first part here. We found that this limit is 5/2. Okay. And we know that this negative 5/2 is where this hole or discontinuity is in the problem. So let's say we're trying to find the limit as x approaches 4. Notice that 4 is a vertical asymptote. So of course, we're not going to be actually getting a value there. It's just whatever it approaches. Well, if we look at this in a small interval, and then look at as x is approaching 4 from the right side, we notice that as it's approaching 4, right side, as it's approaching 4, it's going up towards infinity. And then if I look on the left side, as it's approaching 4, it's going towards negative infinity. Okay. So what this tells us is that if we were to try to do this by direct substitution, we would get something that is undefined. So this would lead to 0 over 0 or undefined. And we can't find the limit of something that is undefined. Okay. So what if they ask you to find a one-sided limit? Okay. For example, here we have the limit as x approaches 4 from the right of the following function. We know that if we were to plug in 4, we would get 0 in the denominator. Okay, we already simplified this in the previous problem, so we know that this is the same as saying the limit as x approaches 4 from the right of x plus 3 over x minus 4. Okay, so if we need to approach it from the right, that means we need to pick a value to the right of 4. Remember, we want it to be as close to 4 as possible. Okay, so we could pick like 4.1. So let's say we do 4.1 plus 3 over 4.1 minus 4. This gives us 7.1 over 0.1, which we know is both positive on the numerator and the denominator, which means as x is approaching 4 from the right side, y is approaching positive infinity. So that's this down here, positive infinity. Now we can do the same thing on the next part. And now we're looking as x approaches 4 from the left side. So we pick a number to the left of 4, which could be 3.9. So 3.9 plus 3 over 3.9 minus 4 gives us 6.9 over negative 0.1, which we know is positive and negative. So the positive on the numerator, negative on the denominator. So this tells us that as x approaches 4 from the left side, y is approaching negative infinity. So the limit as x approaches 4 from the left is negative infinity. Okay. So all this is telling us here is the behavior of the function, not necessarily the value of the limit. Okay. Now in this next one, it says, let's assume that your function is now a piecewise function. Remember, a piecewise function is a function broken up into pieces with different domains. So let's say it wants us to find the limit of g of x as x approaches 1. Well, we have to look at the domains of the function and see where 1 fits in the domain. Well, looking at each of these, it clearly only fits in this one down here because the domain is x is less than or equal to 1, which is where it's approaching 1, which means we only plug it into that one. So we have the limit as x approaches 1 of x plus 1 is equal to 1 plus 1, which is 2. Okay. Same for b. We have the limit of h of x as x approaches 2. Okay, we have two limits here. I'm going to look at as x approaches 2 in the very first domain as x is less than or equal to 2. So we have the limit as x approaches 2 of x squared minus 4x plus 7, which equals 2 squared minus 4 times 2 plus 7, which is 3. Okay. We would notice on both of these problems, so both A and B, if we were to break this up and prove it based on the right and left-sided limits, that we would be getting the same answer on both sides. So if we looked at A and said, okay, what if we looked at as x approaches 1 from the left and as x approaches 1 from the right? Well, we would notice that both of those values would be 2, giving us the limit of 2. Same thing for B. Okay, so more practice on the cancellation technique. Okay. So here, if we were to plug in -4, we would get 0 on the denominator, which means we first need to factor both the numerator and the denominator. So if I was to factor the numerator, I would get 2x minus 1 times x plus 4, and then the denominator would be x minus 5 times x plus 4. If you're still having trouble remembering how to factor, I suggest you go to my Algebra 1 or Algebra 2 playlist and review those topics. Okay. X plus 4 cancels out, which means I am now solving the limit as x approaches -4 of 2x minus 1 over x minus 5. And this is equal to 2 times -4 minus 1 over -4 minus 5. Which gives me, let's see, it's -9 over -9, which is 1. B. In B, we have a difference of cubes. Remember in class I told you that a difference of cubes formula is a minus b times a squared plus ab plus b squared, where a and b are the cube roots of each of these values. So for example, a would be x, because x cubed and the cube root of that would cancel out the exponent. And then b would be 3, because the cube root of 27 is 3. So if I was to factor this, this would be 2x minus 1 times, this would be x minus 3 times x squared plus 3x plus 9 over x minus 3 times x plus 4. The x minus 3 would cancel out, so I would only be finding the limit as x approaches 3 of x squared plus 3x plus 9 over x plus 4, which means I have 3 squared plus 3 times 3 plus 9 over 3 plus 4, which gives me 27/7. Okay. Now let's look at the next method, which is using complex fractions. So for complex fractions, we have to first get rid of all these fractions inside the denominator by getting a common denominator, and then ultimately getting this out by multiplying by the reciprocal. So in order to do this, I'm going to multiply both sides by the opposite denominator. So this is going to be x minus 4, both top and bottom, and this is 4. So I have x minus 4 over 4 times x minus 4 plus 4 over 4 times x minus 4, which gives me x over 4 times x minus 4. That is just the denominator. I still need to bring the numerator back in, so I'm going to do that now. So this is my numerator. In order to get this fraction out of the denominator, I am going to take it and then flip it, or take the reciprocal and then multiply it by that numerator. So this becomes x over 1 times 4 times x minus 4 over x, which means my x's cancel out and I'm left with 4 times x minus 4, which I then take the limit as x approaches 0 and get the value 4 times 0 minus 4, which is negative 16. Okay, I'm going to do the same thing for b. Okay, I'm going to get a common denominator in the numerator. So I'm going to multiply this first one top and bottom by 2 and this next one by 2 plus x. So I have 2 over 2 times 2 plus x minus 2 plus x over 2 times 2 plus x. This is going to give me negative x over 2 times 2 plus x, and then I have to bring in my original denominator of x. So if I flip that and multiply by the reciprocal, I get negative x over 2 times 2 plus x times 1 over x. The x's cancel out and I'm left with negative 1 over 2 times 2 plus x. I can then use that and take the limit as x approaches 0, plug in 0, and I get negative 1 over 2 times 2 plus 0, which is negative 1/4. Okay, next technique here is getting rid of a radical using the conjugate method. Remember, the conjugate means you take the part that has the radical and you multiply the top and bottom by that by only changing this sign. So it's negative, we're going to change it to positive. So our conjugate is going to be the square root of x plus 2 plus 1. Notice that this plus and this minus are opposites. Okay, and then on the bottom, x plus 2 plus 1. Okay, I'm only going to focus on the numerator since the numerator is the one that has the radical. So when I FOIL this, I get x plus 2 squared minus 1. Because 1 is positive and 1 is negative, so this portion right here, I know that when I FOIL it out, the middle terms are going to cancel, so I don't have to worry about those middle terms. This is going to simplify to x plus 2 minus 1, which is x plus 1. So that means I have x plus 1 over x plus 1 times the square root of x plus 2 plus 1. So my x plus 1s are going to cancel out, and I'm left with 1 over the square root of x plus 2 plus 1. And I need to find this as the limit x approaches negative 1. So this is equal to 1 over the square root of negative 1 plus 2 plus 1, which is equal to 1/2. Okay, part B, I'm going to do the same thing. So now my conjugate is going to be 3 plus the square root of x plus 4 on both the top and the bottom. Okay, I'm only going to focus on the denominator since that's the one with my radical, and then I'm going to FOIL those out. So I get 9 minus the square root of x plus 4 squared, which gives me 9 minus x minus 4, which is negative x plus 5. Okay, so that means I have x minus 5 times 3 plus the square root of x plus 4 on my numerator over negative x plus 5. Well, I want to end up canceling out the x minus 5. So what I'm going to do, instead of writing negative x plus 5, I'm going to write it as negative 1 times x minus 5. That way I can cancel out the x minus 5, and I'm left with a 3 plus square root of x plus 4 over negative 1 as the limit as x approaches 5, which means I have 3 plus the square root of 5 plus 4 over negative 1, which is 3 plus 3 over negative 1, which is negative 6. Okay. Continuing on the radical portion here, the big thing is that you need to recall that if you are raising something to an exponent and that exponent is a fraction, that whatever is on the denominator is your radical, okay, or your root. So this 3 is telling us we're taking the cube root. And then whatever number is on the numerator, the top, is still going to be your exponent. Okay, so here we're squaring everything. So we can rewrite this as the limit as x approaches 3 of the cube root of 5x plus 1 squared. Okay, I'm going to try direct substitution and see if I get an answer. So I have the cube root of 5 times 3 plus 1 squared. This is the cube root of 16 squared. The cube root of 16 is not a perfect root, so I'm going to use the prime factor tree. So I have 2 goes into 16 8 times, 2 goes into 8 4 times, and 2 goes into 4 2 times. Circle the 3 2's to take them out. So this is 2 cube root of 2 squared, which gives me 4 cube root of 4 as my answer. Okay. Part B is another conjugate example. So my conjugate is going to be x plus 1 plus 2, and I'm going to multiply the top and bottom by that. Okay. Remember, I'm only focusing on foiling the part that has the radical, so this case it's the numerator, because if I start to foil the denominator, I might miss out on something that I can cancel. So by foiling this, I get the square root of x plus 1 squared minus 4. This simplifies to x plus 1 minus 4, which is x minus 3. So I have x minus 3 over x minus 3 times the square root of x plus 1 plus 2. So I know that these cancel out, and I am left with 1 over the square root of x plus 1 plus 2 as the limit as x approaches 3. So this is 1 over the square root of 4 plus 2, which is 1/4. Okay, now we're on to C. Notice in C, not only does our limit have a directional now, we also notice we have the absolute value function. If you recall, the answer to an absolute value function is always going to be one positive value and one negative value. So I'm going to split this up into two equations. So I have x squared times 2x plus 6 over 4x plus 12. And then I have negative x squared times 2x plus 6 over 4x plus 12. And since one is positive and one is negative, I'm going to set the domains of the first one. The positive one is going to be if x is greater than or equal to negative 3. And then the next one is if x is less than negative 3. Notice, because of this, we just created a piecewise function. So if I was to plug it in to the one that if I was to plug it into the one that is to the left of -3, that would be the negative function, okay? So I'd only be plugging it into this here, okay? So then I would have, before I plug it into this function, before I plugged it into this function, notice that if I was to plug in -3, I would get 0 on the denominator. So I first need to try to cancel something out. Well, if I look at the denominator here, it looks like I could take out a 2, and this would be 2 times 2x plus 6, which would help me cancel out the 2x plus 6 on the numerator. So this would give me -x squared over 2 as the limit as x approaches -3 from the left. And so I would get -3 squared over 2, which is -9/2. Okay. Part D, we're going to do something similar. So we first need to factor or take out the GCF or something to see what can cancel out. So on the bottom here, x squared minus 6x plus 9 is the same as writing x minus 3 squared. And then on the top, I can factor out a GCF of 4, and I'm left with 4 times x minus 3. Okay, so knowing that, if I have 4 times x minus 3 divided by the square root of x minus 3 squared, the square root and the square are going to cancel, and the x minus 3's are going to cancel, which means that the limit as x approaches 3 from the positive side is just going to equal 4. Because what happened here is everything ended up canceling out, and we are just left with the constant function 4. Which means that the limit of anything that x is going to approach is always going to be 4, since 4 is constant. Okay, E is another practice of us doing the getting the common denominator in order to cancel something out. So I'm only focusing on the numerator here. I want to try to get a common denominator. So this one is going to be multiplied by x plus 3 and this one by x. So you can do x plus 3 over x times x plus 3 plus x over x times x plus 3. This is 2x plus 3 over x times x plus 3. All over x. Okay, so I take the reciprocal of the denominator and multiply, so I get 2x plus 3 over x times x plus 3 times 1 over x, which gives me 2x plus 3 over x squared times x plus 3. Okay, notice I can't simplify anything further here. This is as simplified that it's going to get. So from here, I'm just going to have to plug in the limit as x approaches 0. When I do that, I get 3 over 0, which is undefined, which means that if my number is undefined, my limit does not exist. So there might be some cases that even after you do everything possible, nothing is still going to cancel, and you have to plug in that limit, and you're going to get a limit that does not exist. Okay, so it's okay to get an answer that does not exist as long as you've tried everything first. Okay, F. F should look familiar from when we did our pre-assessment and the very beginning, and this is the definition of a derivative. Okay. However, what we need to try to do here is cancel the h out, so when we plug in as h approaches 0, we don't end up with something that is undefined. So first I'm going to FOIL out x plus h squared. So I get x squared plus 2xh plus h squared. Then I'm going to distribute the -3, so I get -3x minus 3h. and then I'm going to distribute the negative, so negative x squared plus 3x. And then I'm just going to start canceling things out that can cancel. So I have a positive 3x and a negative 3x, a negative x squared and a positive x squared. And then that looks like about it. So I'm left with 2xh plus h squared minus 3h all divided by h. In order to cancel out that h, I need to take out a GCF of h. So if I take out an h, I'm left with 2x plus h minus 3 over h. The h's cancel, and so I'm left with the limit as h approaches 0 of 2x plus h minus 3, which is equal to 2x minus 3. Okay. Since this is the definition of a derivative, and we had multiple variables in use, it does make sense to end up with a function as our limit. Okay. And then lastly, we're going to talk about the squeeze theorem. So ultimately what the squeeze theorem is this tells us that if we are trying to find the limit of a function, we can squeeze it between two functions that we already know the limit, and we will be able to find that limit of the function as long as all of those limits equal one value, and in this theorem they call that value L. So here is the diagram of what it's talking about. So the g of x portion is the one we don't know. Okay, h of x and f of x we do know. Okay, so if we try to squeeze h of x and f of x together so it gets very, very close to g of x, we will notice that as the limit approaches a value c, that limit will all exist at the same value L. Okay. So looking at an example, it says if 1 is less than or equal to f of x is less than or equal to x squared plus 2x plus 2, find the limit as x approaches negative 1 of f of x. So what we're doing is we're finding the limit of each of them. So the limit as x approaches negative 1 of 1 is less than or equal to the limit as x approaches negative 1 of f of x is less than or equal to the limit as x approaches negative 1 of x squared plus 2x plus 2. Well, the first part here is the limit of a constant function. So we know that is 1. So 1 is less than or equal to the limit as x approaches negative 1 of f of x is less than or equal to, and then here we're just plugging in negative 1 for the x's. So negative 1 squared plus 2 times negative 1 plus 2, that gives us 1. So by the squeeze theorem, the limit as x approaches negative 1 of f of x is also 1. Okay. So let's further discuss this and look at a proof using this example here. So it says given that f of x is equal to the natural log of x plus x squared and g of x is equal to e to the power of x minus 1 for all x in the interval containing x equals 1 except possibly at x equals 1 itself, find the limit as x approaches 1 of h of x and justify. That justify is our proof. Okay. So starting off, we're going to say, notice the limit at x equals 1 on f of x and g of x are both 1, but f of x and g of x change at x equals 1. So what that's saying is, looking at the graph here, okay, if we look at the value of 1, it looks like all of them equal 1. But once we pass that, they all started going in different directions. So this one is starting to go up in a curve. The one that we're squeezing and trying to find is kind of doing a little squiggle, and then the other one looks like it's about almost going like a linear type way. They're all going in different directions. Okay, so what we're going to do is we are going to find the limit of f of x and g of x as x approaches 1. So by looking at the graph, we know that the limit as x approaches 1 of f of x is equal to 1, and the limit as x approaches 1 of g of x is equal to 1. Well, in order to prove that we can use the squeeze theorem to find the limit of h of x, we have to look at the values on either side, the left and the right. So for x less than 1, f of x has to be less than or equal to h of x less than or equal to g of x. And since the limit as x approaches 1 from the left of f of x is equal to 1, which is also the limit as x approaches 1 from the left of g of x, this tells us that the limit as x approaches 1 from the left of h of x is also equal to 1. So we proved just the left side. Now we have to prove the right side. So the opposite, for x greater than 1, we have to show that g of x is less than or equal to h of x less than or equal to f of x. So we would say since the limit as x approaches 1 from the right side of g of x is equal to 1, which is the limit as x approaches 1 from the right side of f of x, is also equal to 1. This implies that the limit as x approaches 1 from the right side of h of x is equal to 1. Okay. Therefore, that's what those dots stand for. Therefore, that if the limit therefore the limit as x approaches 1 from the left side of h of x is equal to the limit as x approaches 1 from the right side of h of x is the same value 1 by the squeeze theorem. The limit as x approaches 1 of h of x is equal to 1. End of proof.